All right, people, we got a little packet here. Actually, let me quick run, grab a piece of paper so I can kind of annotate some things here. So this packet is a little bit longer one, but I think we'll get through it pretty quickly. But I want to give you just kind of an overview of the whole thing here really quick. You can read the details, and we're going to work through the problems here in class, and in the next few days we'll get through this. And then worksheet 3 is the next one. There's some review questions, but worksheet 2 here is all about work. Calculating the work done by forces, the work done by net forces, by individual forces, and so on. So big picture here is that, remember, forces are what cause changes in energy, right? Forces drive energy transfer. So when we looked at the bar graphs, right, what makes a object starts off PEG, whoops, I should have done UG. What makes an object transfer its energy from potential energy into kinetic, right? What makes it go from one into the other? And the answer is the force of gravity, right? Force of gravity pulls the object down, applies a force, does work on the object. The amount of work that the gravity does is the force of gravity multiplied by whatever the displacement is, which you could call delta Y if you wished, or you could call delta H, right? And usually we just call it like work equals Fg delta Y, or, which ends up being, H. But there's a little more to it. Usually we just kind of treat it very loosely like that, force times distance. We get the work done. And we say that equals the change in kinetic energy. All right? So whatever work is done causes the kinetic energy to change. Now, I'm using PEG, KE, I'll try to get UG and capital K, but it's hard to switch. It's hard to switch between the different classes. So it is a little more specific than this, okay? Let's look at a box sitting on a table or something, okay? No friction. We'll pull it straight, okay? Let's say the force is 10 newtons, the mass is 1 kilogram, and it displaces itself 1 meter, all right? Let's say it gets displaced over to here. So the displacement vector is right here. This is the force vector, positive 10. The displacement vector, we'll call it delta x, equals positive 1 meter. The work done, we simply usually just say it's the force times the distance, right? 10 newtons times 1 meter, so it's plus 10 joules. Well, that's fine and all. And then we could say, okay, that equals the change in kinetic energy, delta KE, which is 1/2 mv final squared minus 1/2 mv initial squared. And it is important to realize that it's not 1/2 m delta v squared. We'll talk about that in class at some point. It actually ends up being 1/2 of m times v final squared minus v initial squared. You can't actually put delta v squared in there. It's a totally different equation if you do. Now, that's cool. All right, displaced itself that way, accelerated it, plus 10 joules. And it does come out positive, right? Well, what if we did this? What if it was a block sliding this way, right? Let's say it was already sliding this way, and it displaced itself positive 1 meter that way. So let's say it started off with some kinetic energy. So this one started off with no kinetic energy, and I pulled it. Let's say this one started off with some kinetic energy, and I pulled it the opposite way. So I pulled it this way with a force of negative 10 newtons, right? Well, what would the work be? It would be negative 10 joules. So that would be the change in kinetic energy of that object would be negative 10 joules. It's sliding this way, the force is going that way, it's going to take kinetic energy away. How do I prove that mathematically? That it should be negative 10. Well, you would say, okay, work is force times distance, and or force delta x, and that's going to be negative, the force, and delta x is positive. So really what you're doing is you're treating them as vectors, right? And you're actually, you're actually treating them as vector quantities. So the work done here is F times displacement. So by making them positive and negative, you're treating them like vector quantities. Now, that kind of brings us to the next problem. Okay, well, what do you do if that force is at an angle, right? And those of you that took Physics 11H, you might remember one of the first force problems we did was somebody pulling something at an angle, theta, right? Well, let's say it's the same displacement, right? So the displacement vector, I'm drawing the displacement as a vector here. Looks like that. This is the force vector. Well, how do you figure out the work done? You can't just do this force times that distance because not all of that force is going into displacing it, right? Some of that force is going into against gravity. So really what you need to find is you need to find the component of the angled force that is parallel to the displacement, which in this case would be Fx, right? The x component of the force, right? So really in this case the work ends up being Fx times delta x. All right, so you got to find the component of this force, of the applied force, that is parallel to the displacement, and then multiply those two together. Well, there's a mathematical term for this. It's called the dot product. All right, the dot product. And I try to describe it. Dot product of two vectors. All right, and kind of the generic illustration is, okay, if you have vector A and vector B, let's say, right, we write it like this: A dot B equals, well, you have to find, and this is the angle theta, right? You got to find the projection of A onto B. So that's, we call that sometimes A parallel, the parallel component. Well, that is going to be A times the cos of theta. That's going to be that component times B, right? We usually write it as A, to make it look a little neater, B cos of the angle between them, right? And this is the magnitude. It's just the length of this line multiplied by the length of this line multiplied by the cos of the angle between them. So you don't find the component of A and then do the cos again. This cos theta is taking into account, the fact that you're finding the component of A parallel to B. And when this angle is less than 90, if theta is less than 90, the dot product comes out to be positive. If theta is greater than 90, the dot product comes out to be negative, which is, if we go back and look at this problem, right? And we use the dot product to figure it out, we would say work equals F, magnitude of F, times the magnitude of the displacement, times cos of the angle between them. Well, the angle between them is 0, so the cos is 1. So it literally is just force times distance. If we look at this one, right, it'd be work equals the magnitude of F, which is negative 10, times the magnitude of displacement, positive 1, right, times the cos of the angle between them. Well, the cos of the angle between these is 180, right? In this case, it would be cos of 180. This would be cos of 0, and that is negative 1. So you get negative 10 joules. It's pretty cool that way. The way that the math will work out, the sign of the work would work out from the angle between the two forces. Really neat that way. And then this shows why a force pulling up doesn't do any work, because that angle then is 90, right? And that would be 0, no work done. Pretty cool. So that's a dot product. That's how we calculate the work done by a particular force. Now the last thing I want to talk about quick in this video, before I got to get to lunch duty here, this will be a little shorter one today, is just the idea of kind of the idea of, it's kind of like that tank problem we did where, you know, if you look at an object, right, and you look at, you know, the bar diagram, like, you know, let's say something starts with a whole bunch of potential energy, right, P, U, G, right, and then in whatever it is, it ends up with, less UG, right, let's say it ends up with some KE, maybe 1 unit of KE, but then a whole bunch of 2 units of E internal, right? E internal, right? So there's all kinds of work done. The gravity did work to pull it down, right? Friction did work, did work and slowed it down. And then overall, whatever the net change in kinetic energy is, no matter all the other energies, that's the net work. Whatever the change in kinetic energy is your net work, and that's always equal to the net force times the displacement. And we use delta R because we don't know if it's X, Y, Z, whatever. Delta R times the cos of theta. This can be a multi-dimensional vector. For instance, you could have a force of A I hat plus B J hat plus C K hat for your force, right? And then, so this is kind of cool. That vector dot, let's say the radius vector was D I hat plus E J hat plus F K hat. The dot product is simply you multiply the like terms, right? And what's kind of cool is, let's say there was no, let's say the radius, right? Let's actually say, well, what you get is you multiply the like coefficient, so it'd be AD plus the product of BE plus the product of C and F. And it ends up being a scalar, no vector, just a sum. Now, what's kind of cool about that, you can instantly see if one of the, let's say there was no Y and Z components to displacement. It was a 3-dimensional force, but it only moved in the X direction. Like, so let's say that was the coefficients are 0 for these two terms. Well, these two terms would both be 0, and we'd only have these two terms. And well, that's good because this is the only component that's parallel, that are parallel. A is the only component that has a that is parallel to the displacement D. You know, so it would be just AD. So in vector notation has rules for dot product. We're not really gonna get into that. It's just kind of interesting. And finally, I said this was the last thing, but kind of goes along with this though. Look at the difference between, let's take out, you know, let's call this U internal, right? Let's take that out. Let's just look at a system where it's an object falling really quick, okay? So an object falls down, right? Gains speed, hits the ground. All right, so it starts off all UG, gets converted into all kinetic. All right? So let's say we started off with, you know, I guess I should consider UG here and K here. Say I start off with 100 joules of gravitational energy. So as it goes from here to here, what's its change in kinetic energy? Change in kinetic energy is plus 100 joules. It gained energy. Gravity did work on it. What's the change in potential energy of the object? It's negative 100 joules. All right? So sometimes we see this formula that looks like this. We say, all right, we say work equals change in kinetic energy equals negative change in gravitational energy. All right, we see that sometimes. And that's important, believe it or not. And that can also be, again, F dot delta R, right? So the work can be equal to the negative change in potential energy. That's something we do often see. One, I suppose, I keep saying one last thing, but the other big picture thing here is that, well, I guess I'll save that for for the next video. All right, which will be talk a little bit about the calculus and function aspect of this. So let's just get this basic stuff down, then we'll talk about a little bit more later on about the calculus aspect of this worksheet. All right, turns out that this force here, right, is not always constant. Sometimes there's a time varying force. So you can't just do FR. Oops, I shouldn't have written that like that. It should have been F dot R without the magnitude there, F dot delta R. Turns out you can't always just multiply the two. You have to sometimes take the integral of force and replace the delta with a D. The dot is still there, dr. You know, so if it's a constant force, that's fine. But if it's a varying force, you have to take the integral. It's all about finding the area under the curve, which we'll see in the next video.